So this was a big group, and it was a big sort of concoction of items we had from the brainstorming sessions that we talked about. It included Niklas as well, although Niklas and Linus were in parallel doing their topic that we just saw. But there was some interaction. TC took part, and Juan, Mikkel Likkegaard, and then Hermann Mattis, Fabio Nobile, Benjamin Beersdorf, Paul Rohrbach, and Elisabeth Ullmann as well. So what did we talk about beyond plain vanilla multi-level, multi-index? So it's not so far beyond multi-level, multi-index, but maybe beyond plain vanilla. And we discussed the topics that came up in the brainstorming sessions and homed in on two. One is the thing that I will talk about now, which is namely multi-level, multi-index for problems with, I always call it a homotopy parameter. So if you have a hard problem you want to solve, a hard nonlinear problem, for example, and you have a sequence of easier problems or a sequence of problems that get successively harder, then that's a nice hierarchy that you can use for potentially doing multi-level or multi-index, Monte Carlo, or any multi-fidelity, multi-level method. And it is actually the method of choice, for example, in nonlinear elasticity or in regularized optimization of regularized minimization problems. It is often the method of choice to do continuation. So here is just this problem. So you have a homotopy parameter T. You're interested in, for example, some expected value of some functional of the solution of this problem at homotopy parameter 1. And you're solving it for coarser one. So the idea would be to use a hierarchy of these homotopy parameters, similar to what Benjamin talked about. So you'd probably have some geometric progression towards the last, towards 1 to make a gain with your multi-level method. It could be, as I said, the regularization parameter in an optimization problem that gets harder to solve for low regularization. It could be, that's now referring to the talk before, it could be the strength of the advection of the nonlinear reaction term in an advection reaction diffusion problem. As we already saw, and as we identified in the discussions already, changing the strength of the advection will probably not work in a multi-index way. It could be the loading in a nonlinear elasticity problem or the box size in Paul's particle system. And then the other topics we discussed was the second point that Niklas referred to. We also discussed about MLMC when you have some stability constraints and you need to have sample adaptive choice of the coarsest level. And I asked him to try it out with his code, so we will probably follow this up at some point. So I come to the multi-index. So this is just if you have several discretization parameters, and when I say discretization, I really mean this in the widest sense of the word. So it could be simply different models and in particular, for example, this homotopy idea, the homotopy parameter, but it can be also spatial mesh size, time step, domain size, etc. And then the multi-index, we've seen it already today. You replace the single difference by a double difference. So you combine a difference in one of the discretization indices with the discretization in the second index in this product way. And so you get a sort of double difference. One example would be the coarsening of a finite element mesh in X direction and in Y direction. And then you get this picture that Abdul already showed, where you get these squares in 2D, where you average over or you do double difference. You then, as Abdul showed, do the expected value of these differences instead of the expected value directly. And if you want to simulate with mesh size or with discretization parameter L1 and L2, capital L1, capital L2, then you'd simply add all those up. And that would be the plain vanilla MIMC. But the one thing we already said in Abdul's talk is that the real gain comes from the fact that you can actually use this total degree set, provided you have sufficient regularity, and you never need to compute up in this corner. You essentially only work in the lower corner, and depending on the smoothness and on the weights in the two in the two rates, this triangle can be more flat or more steep. Okay, now one concrete outcome of the working group is that there's definitely one place where we think we can apply multi-index, or to expand on something that Paul told us about. So for example, so Paul talked about these particle systems with coarse-grained models, and then a very expensive way of filling in the small particles, which are 1/10 of the size of the coarse particles, and having a multi-level or two-level method, a three-level method doing this. But obviously one error that's in these systems still is the finite box size. There's periodic boundary conditions on the box. And for especially the quantity of interest, which was the pairwise correlation function of the coarse particles, you really want the infinite dimensional system. So you can do a homotopy, if I stick with my word, over the domain size. And if you have that, you get a small coarse graining error, and you get a small error due to the domain truncation if the smallest of the two is not too small. Then essentially the double difference idea is that if you take the difference of the differences, then if you have sufficient smoothness, the errors multiply, and so you get a second order contribution to your estimator in your sum of the telescoping sum. So you could just set that to 0 because it's lower order in comparison to the other two. And then you have a method of solving for the finest system here without ever touching it. Okay, so and this is, I think this is one of the really beauties of the multi-index approach beyond the variance reduction, for which you really need often quite a lot. You don't often get that much extra over multi-level, but in a physics situation where a big box with this method simply is not feasible, is a huge gain if you only have to solve these 3 boxes and you get the accuracy of this one essentially up to second order terms. Other systems we discussed were I already mentioned, the nonlinear elasticity, where in engineering, typically methods always use some incremental loading of a beam, and then you solve harder and harder nonlinear problems, and you need more and more work because you need to do the whole trajectory if there's a random sample you're solving. And another example was the nonlinearity in this approximations of this ice sheet dynamics, where you've got a P Laplacian. So the diffusion coefficient depends on the gradient of the solution to some power P. And again, you can do a homotopy potentially over the P. But as I said, it's quite problem specific, but I really think it would be nice to write this down in a formal way, because it would be, there could be plenty of examples where you have this mixed regularity, at least to some extent, and you can really gain from this multi-index. I hand over to Abdul, or shall I just say it? So basically what we did not discuss much, but which is going beyond what we discussed, is that above we had examples where it was a clear hierarchy, typically the cost and or the hardness of the problem. But when you don't have that, then obviously the MIMC framework will probably get onto its limits. And so one could then do exactly what we've heard already several times from Benjamin and others. I open everything up. Also from Elizabeth with her multi-level blue estimator, which we had in the 2020 workshop. You can basically try to find the optimal covariance structure between these terms, and to some extent, you could try and find the double difference between your models if you don't know it a priori. okay? Or at least you can get the most out of your hierarchy of models. That's basically what we discussed in that theme. Is there anything I forgot? There was a big group, so no. Okay, any questions to that theme? Okay, so the last thing I wanted to say before I wrap up is I wanted to just acknowledge all the themes that we came up with, and also encourage people to not let it completely get lost, the plans and ideas. So I was just summarizing what we have on our Google Docs spreadsheet. So everybody, I think, has the link to it, so you can look back. There's email addresses there, so you can hook up. I'm not gonna take any control of this. I'm definitely gonna continue with Abdo on the multi-index delayed acceptance, because that's what I'm most excited about, and I will probably continue talking to Niklas about this other problem via Linus. So, but there is other topics. For example, the first one, where there was quite a few people interested, but we couldn't fit that in. In particular, there was quite a few people also from the online audience interested in adaptivity, and by this we mean all sorts of adaptivity, spatial or discretization adaptivity, but also model adaptivity, reduced order modeling adaptivity, etc. The second one was chaotic systems and systems that are difficult to couple pathwise. So again, there was quite a few people showing interest there. And I was gonna encourage people to get in touch with each other. This one was the first one presented today by Håkon. And there is one name, I just put the plus, the guys that were not here, so that you don't forget them. So Neil had his name down against that one. So if you do continue talking, maybe involve him. And then another topic we didn't have time to talk about was the path branching idea that Abdo talked about. And there is a couple of people who showed interest here. And I'll leave that with Abdo to organize if he wants to. And TC has already taken on himself to organize, to discuss with Håkon and Elizabeth Kian on the randomized and optimized approach for Bayesian inverse problems. These are topics we discussed. Bariza Kodabakshi was interested in getting involved in the multi-level delayed acceptance. So please email us if you do want to. The fault tolerance. So there's two topics that had less of a take-up, which was probably mostly due to the audience and the people's interests. So both of the sort of more programming type things, fault tolerance and parallelization issues, had less of an uptake. That's not to say that they're not important, but we have not talked about them or created any groups here. And that's it. So for the other two topics that were discussed in the second session now, please don't forget those people from across the ocean and from Italy in communications about these themes as well. Okay, so that's what this whole interactive activity created. I hope you enjoyed it. I hope you actually got some stimulating stuff going. I certainly had some very interesting discussions. Like we said, this board here describes only in bits how much we've wrapped off and put on again. But I think it was very exciting, and thanks for contributing to it.